Summarizing quantitative data. Frequency, relative frequency, and percent frequency distributions are also used to summarize quantitative data in addition to qualitative data. The challenge in using these distributions to summarize quantitative data lies in the process for defining non-overlapping classes for our data. Recall, for qualitative data, we define classes based upon all of the possible response categories in our data. If we had quantitative data, such as the grades that students earned on an exam, grades could range from 0 to 100. If we define classes in the same manner that we did for qualitative data, we would have 101 different classes ranging from 0 up to 100. More than likely, the overwhelming majority of our classes will have a height of 1. Having a lot of classes with the same height would not provide insight into patterns that exist within our data set. On the other hand, if we defined our classes using too few classes, this would also not be useful. For instance, if we defined one class as all grades ranging from 0 to 50, and the other class for grades above 50 up to 100, hopefully the majority of our grades would fall in the latter class. Having two classes where one has a height that is relatively small and the other contain the overwhelming majority of data values from our data set would not provide useful information. For quantitative data, classes are interval ranges in which data can fall. Classes must be defined so that, number one, all classes have equal width. The width is a difference between the lower limit of two successive classes. In other words, you would not want to define your first class as grades from 0 up to 15, the next class from 15 up to 50, the third class from 50 up to 90, and the last class from 90 to 100. Instead, you would want all of your classes to have equal width. The second requirement is that there must be no gaps between your classes. Having one class range from 0 to 10 and the next begin at 12 ranging to 22 would leave a gap for potential values to fall between. Our third criterion: all of our classes must be non-overlapping, and all potential measurements must have exactly one class in which it falls. For instance, we would not want to define one class as values from 0 to 15, and the second class as values from 13 to 28. Technically, as long as we define our classes in a manner in which all three of these criteria are met, then our classifications would actually be valid. There is no unique method in which classes must be defined, as long as these rules are met. On the following slides, we are going to provide one technique for defining classes in a manner which usually produces useful results. Here, we define a three-step process for defining classes. In step 1, we should determine the number of classes that we want to use. As previously mentioned, we don't want to use too few or too many classes. Step 2, we should set our class width value. And in step 3, we actually define the lower and upper limits for our classes. First, let's focus on step 1, determining the number of classes that we should use. Here is a basic rule that I found in Bowerman's statistics book that helps students with determining the number of classes that they should use. The rule says that the number of classes should be the smallest whole number k that makes 2 to the k power greater than the total number of measurements n. If we apply that rule here in example 1, we should try to determine the number of classes that we should use to summarize 25 data values. Using Bowerman's rule, our n value is 25. We can start off with the k value of 1 as our exponent for 2. 2 to the first power is equal to 2. That value is not greater than our number of data values n equals 25. So we should increase k to 2. 2 to the second power is equal to 4. This number is also not greater than n equals 25, our number of data values. So let's increase k to 3. 2 to the third power equals 8, still not greater than 25. We increase k to 4. 2 to the fourth power equals 16, still not greater than 25, so we increase k to 5. 2 to the fifth power is 32. This number is now greater than our n equals 25 data values. Therefore, we should use k equals 5 classes to summarize our n equals 25 data values. Let's try step 1 again for a different example. Using Bowerman's rule, how many classes should we use to summarize 50 data values? Using Bowerman's rule, n equals 50. If we start out with k equals 1 as the exponent for our base 2, 2 to the first power is not greater than our n equals 50 data values. 2 to the second power equals 4, still not greater than 50. 2 to the third power equals 8, still not greater than our n equals 50 data values. 2 to the fourth power is 16. 2 to the fifth power is 32. 2 to the sixth power is 64. 64 is the first number that we encounter that is greater than our n equals 50 data values. Therefore, we should use k equals 6 classes to summarize our n equals 50 data values. Using Bowerman's rule, let's take a moment and try out an example to see if you can correctly determine the number of classes that we should use to summarize 250 data values. You should pause the video at this time and try this example on your own. Using Bowerman's rule, you should have started with a k value of 1 and incremented k all the way up to a k value of 8. That is the smallest integer such that 2 to the k power is greater than our n equals 250 data values. 2 to the 7th power was only 128, but 2 to the 8th power was equal to 256. A number that is greater than our n equals 250 data values. Therefore, we should use k equals 8 classes to summarize our 250 data values. Now let's focus on step 2, setting our class width. We should set our class width as the largest measurement minus the smallest measurement plus 0.05. All of this divided by k, the number of classes that we defined in step 1. This formula is slightly different than most formulas that you may encounter for class width. We chose to add this 0.05 nudging factor to this difference in the numerator based upon past experience. Based upon past experience, we have found that without this small nudging factor, it was possible to compute the class width and get an integer value. Using the procedures outlined here in this section, that would have caused our largest measurement in our data set not to have a category to fall. That largest data value would have actually been above the upper limit for our largest class width. Adding this small nudging factor there corrects this problem. Please note that once you compute your class width, you will likely get a decimal value, a whole number with a decimal value. You can always round this number up to the nearest integer in order to simplify the creation of classes. You can never round the number down. So even if you end up with a class width value of 10.2, you can round that number up to 10.5 or round it up to 11 in order to simplify our process. However, you should never round that number down to 10. We put this comment here in red on this slide just to remind you that normal rounding rules should not be applied in this situation. Step 3 for creating classes. It's now time to set our lower and upper limits for classes. When creating our lower and upper limits, we start by using our smallest measurement and setting that as the lower limit for our first class. Next, we define the lower limits for the remaining classes by adding the lower limit of the preceding class and the selected class width. Last, we define the upper limit for each class as the largest potential measurement less than the lower limit of the following class. The purpose of step 3 is to ensure that there are no gaps between our classes. Even though these steps may seem difficult when putting them into words on this slide, we will do several examples to practice and show you that implementing this process is not very difficult. Let's look at this example. A cell phone company implemented a major advertising campaign. They recorded the number of new customers each day for the first 30 days following the implementation of the campaign. The results are provided on this slide. We want to create a frequency distribution for this data. Using our steps, we should first determine the number of classes to use for our n equals 30 data values. Using Bowerman's rule, 2 to the 4th power is 16, 2 to the 5th power is 32. 32 is larger than our n equals 30 data values. Therefore, we should use k equals 5 classes in order to summarize our data. Next, we determine the class width. Recall our formula for class width tells us to use our largest value in the data set. Our largest value is 18 minus the smallest value in our data set. Our smallest value is 5 plus 0.01 divided by k equals 5, the number of classes that we selected in our first step. This equals 2.61. Recall, we can always round up our class width to the nearest integer to simplify our process. Now, in our last step, we create the lower and upper limits for each class. Since 5 is the smallest measurement, this should be the lower limit for our first class. Now, in order to create the lower limits for our other classes, we should add the class width onto the lower limit for the first class. Our class width is 3, so the lowest limit for our first class is 5, our smallest measurements, plus 3 gives us 8 as the lower limit for the next class, plus our width 3 gives us 11 as the lower limit for our next class, plus 3 equals 14, which gives us our next lowest limit, plus 3 equals 17, which gives us our last lowest limit or lower limit for our class. Now that we have our lower limits, we need to create the upper limit for each class in a manner that ensures that there's no gaps between our classes. Therefore, in order to create the upper limit for our first class, I need to look at the lower limit for the next class. I want to create my upper limit so that there's no gap between 8 and the upper limit that I set for this class. In order to do this, I set my upper limit for my first class as 7.999. I set this upper limit because I know that there is no way that a value in my data set could fall between 7.999 and 8, the lower limit for the next class. I can add my class width onto the upper limit of the first class in order to get my upper limits for the remaining classes. Now that we have defined our classes, we should determine the frequency for each of these classes. For our first class, 5 to 7.999, our frequency is 6. If we go back to our original data set, we will see that there are exactly 6 values in this data that fall between 5 and 7.99. Our frequency for the class 8 to 10.99 is 13, because there are exactly 13 values that fall between 8 and 10.999. We continue that process of looking through our data set to determine the number of values that fall in each of these intervals in order to write the frequency for the remaining classes. If we sum the frequencies for all of our classes, we should get the total number of measurements. Once we have our frequency distributions, we can then compute our relative frequency distribution. Recall, our relative frequency for a class is just the fraction of all values in our data set that falls within that class. Our relative frequency for the class 5 to 7.99 is 6 divided by 30. Our relative frequency for the class 8 to 10.99 is 13 divided by 30. When we sum the relative frequencies for all of our classes, we obtain 1. Just to note again, the sum of all frequencies should always equal n, the total number of data values, and the sum of all relative frequencies should always equal 1. Now let's get some hands-on practice with creating classes for our quantitative data. The manager of Hudson Auto would like to get a better picture of the distribution of costs for engine tune-up parts. A sample of 50 customer invoices has been taken, and the costs of parts are listed in this table below. We should pause the video at this time and compute the classes in order to summarize this data. In step 1, you should have used Bowerman's rule to determine that k equals 6 classes should be used to summarize our n equals 50 data values. In step 2, in determining our class width, we should have noticed that in our data set, 52 was the smallest measurement, 109.4 was the largest measurement, and so our class width should be computed as our largest measurement, 109.4, minus our smallest measurement, 52, plus 0.05 divided by our k value, which is 6. This gives us a width of 9.58. We're going to round this value up to 10 in order to simplify the creation of our classes. You should have began by defining 52 as the lower limit for your first class, then added your class width in order to get the lower limits for the following classes. 52, 62, 72, 82, 92, and 102 should have been the lower limits for your 6 classes. Next, you should have defined your upper limits for the classes based upon the smallest value that could occur smaller than the lower limit for the next class. The next smallest value from 62 should have defined our upper limit for this class, and that upper limit should have been defined as 61.999. You should have added your class width in order to get the upper limits for the other classes. Now that we have the classes defined for our data, we can go into our original data and count up the number of values that fall in each of these classes in order to obtain our frequency. You can pause the video again at this time and go back to the original data set and try to accurately compute the frequency for each of these classes. You should have obtained these frequencies for each class. We could then go on to compute the relative frequency for each class. Just to ensure that we did count all of our numbers accurately, you can sum the frequency for your classes to obtain 50, the number of data values in our set, and verify that the relative frequencies do sum to 1. A histogram is the name that we give for bar graphs that represents quantitative data. Two major differences between a bar graph and a histogram is, number one, there should be no natural separations between your classes or the rectangles that represent each class. This signifies that there are no gaps between our classes. Notice, when doing a histogram for our data, we made sure that there were no gaps between our classes. Also, similar to the bar graph for qualitative data, all of our bars had an equal width. A second major difference between a bar graph for qualitative data and a histogram for quantitative data is the fact that our x-axis actually represents data values, a continuous interval. Unlike qualitative data, we do not simply place the label of each class under each bar. Instead, we have our x-axis. The beginning of the bar for each class should begin at the starting point for the interval that that class represents, and that bar should continue to the upper limit of the interval that that bar represents. The height of each bar should represent the frequency, relative frequency, or percent frequency for each class. Our first class goes from 52 all the way up to 61.99, the value that falls right before 62. And it has a height of frequency 2. Our second class begins at 62 and goes all the way up until, but not including, 72. And the height matches the frequency for that class. Again, let's get some hands-on practice doing a relative frequency distribution and a histogram from the start with this data set presented on this slide. We'll begin with creating our classes, then compute your frequency distribution, your relative frequency distribution, and then do a histogram. You should pause the video at this time and follow the steps outlined in this section. You should have started by determining that we should use k equals 5 classes in order to summarize our n equals 30 data values. You then should have computed your class width to be 4.97. In order to make our process of defining classes easier, you should have rounded this value up to 5. Next, you should have started with 17.2 in creating the lower limit for your first class. You should have created the other lower limits for your classes by adding your class width to 17.2. Your lower limit should be 17.2, 22.2, 27.2, 32.2, and 37.2. You should have created your upper limits in order to ensure that there were no gaps between your classes. Your upper limit should be 22.1999, 27.1999, 32.1999, 37.1999, and 42.1999. The reason I selected 22.199 as my upper limit is because that is the smallest number from 22.2 that I could write, that I could easily write. Now, you should have computed your frequencies and relative frequencies for all classes as shown on this slide. I created a histogram using the frequency distribution, and your histogram should look like this. You didn't have to use the same values that I used on my x-axis, but it should be apparent that each of your classes begin at the lower limit and end at the upper limit for each of your classes.